Okay, so let's start. So I'll first talk about how I want to go about in this course. So I'll start off with, say, the first part would be discrete random variables. So when we'll be learning discrete random variables, we'll have some basic counting. We'll learn some basic combinatorics. Okay, first. So basic counting principles. Then we'll probably go to generalized. Yeah. So generalized counting principles, and then we'll know about multinomial coefficients. Okay, and then we'll go to the probability setup. So this is basic combinatorics. Then we'll go to the probability setup. So like, so basic notion. Then sets and axioms of probability. And finally, uniform discrete distribution. So this will be our basic probability setup. Oh, okay. So okay, so let's directly go to discrete random variables then, right? So you have covered till that, right? Okay, okay. So say we define. So you know what is a sample space, right? So let S be a sample space. So what is a random variable? A random variable is a real valued function on this sample space. Is this sample space. Random variables, say we usually define it by some alphabets, say capital alphabets, x, y, z, and a discrete random variable is one that can take on only countably many values from this sample space, right? So we usually denote it by some, say, capital letters, and a discrete random variable is a random variable which can take on only countably many values. Right. So some examples. Right. So say example one. If I roll a dice uh, and say X denotes the outcome, so what would the values for X? The values for X would be 1, 2, 3, 4, 5, 6, right? So X can take on values 1, 2, 3, 4, 5, 6. Say if I roll a dice again, and if I get an even number, I say Y is equal to 1. Otherwise, if it is odd, we say Y equals 0. So that is also another random variable, right? So if the event is, if it is even, then we say that it is 1, and if it is odd, we say that it is 0, right? For example, if we toss heads, if we toss, if we toss a coin 10 times, so the number of heads, say Z. So that is a random variable, right? It can vary from 0 to 10. Now uh, say there are n uh, experiments, then the number of successes, similar to the previous one, right? So and notice that these all are discrete random variables, like they're taking on countably many values, right? So these are some examples of discrete random variables. Now we need to define what is a PMF, or density of a random variable. So PMF, which is called the probability mass function, or the density of a random variable. It is also called density. At least at this moment. So for a discrete random variable X, the PMF of X is defined by So this is the probability sign, right? So this is nothing but this means the probability that the random variable is having this state in the sample space, right? So you can like so you can say that this can be termed as a pre-image, right? The pre-image of this is the event. What is the event? Uh, the pre-image of this is the event, right? So the event is where S is my sample space, for which this happens, right?
So shouldn't W be in R?
This should be X.
Oh yeah.
Yeah. So the pre-image of this, yeah. This means all those omegas in the sample space for which this happens, right? So suppose uh, X is a discrete random variable taking on values like this, like it's a sequence, like count, and it's a countable sequence, then the PMF would be defined something like this, right? I mean, a property of the PMFs. Since this is what we defined our probability on, so the whole space should be one, and this is how I am defining the probability mass function. So summing them up should come up to be one, right? So let's check an example. Like, so let X denote the number when we roll a die. So the expected number, so let me write this like this: the expected number that should show up on a roll of a die what should that be? What should be the expected uh, number that should show up on a die? That should be something like this, right? So I denoted X as the number when we rolled a die. So plus, right? So this comes out to be 3.5, right? because all of these are equal probability, so 1 by 6 and sum them up. So what can be a general definition of expectation from this for a discrete random variable, say? So we defined PMF. We define random variables and discrete random variables. So now we need to define expectation of a discrete random variable, right? So expectation of a discrete random variable.
Sigma x into p of x.
Could you repeat
Yeah,
once?
sigma I into p of x equal to I, where I runs for all the values
Y runs for all the values
in the
which are
sample space. In the sample space.
in the sample space. Uh, right. But yeah. So okay. So I'll write the definition that you're saying, and I'll write this one. So just there's a subtle difference. So just notice that. So uh, we define expectation of x as summation. This is fine. Now where does this summation run on? So x such that so you notice a subtle change.
Only for positive values of.
Yeah. So only the things which have a positive measure. So we'll come to that later on. And what you are saying is actually correct. So both of them are correct, but you only need to define it on a set of. I mean, you don't need to define. Need to worry about the sets of zero measure. Okay. So
Yeah.
that's fine. But yeah. So expectation of a discrete random variable is defined like this. Provided provided what? Provided this sum converges absolutely, right? Because otherwise it's not defined. In this case, we say that it is well defined. But if it does not converge, then it is not well defined, right? So we should have this summation to converge absolutely, right? Like, okay, so why is this true? Why do we need this to be true? So let's see. The expectation should not depend on the order in which we take the sum, right?
Yes, sir.
So the expectation should not depend on the order of the sum. Now you have learned about convergent sequences, right? And conditionally convergent sequences and absolutely convergent sequences. So in case of a conditionally convergent sequence, we need to be careful, right? Because see, the this is summation x times px, right? So this is essentially summation this, right? So now this is positive, but this can be negative, right? So in general, the terms in this summation might have different signs. So then the order will matter, which we do not want. Then we will have different expectations, right? Depending on the order. So that is why we need this. So this is very important that we need this sum to converge absolutely. Okay. So let's try a problem then. If we toss a coin and x is 1 if we have heads, and 0 if we have tails. So what is the expectation of x?
Sure, half.
Yeah. So just this is basically right.
Yes.
Now, yeah, yeah. Hello, I couldn't hear you.
Yes, it's fine.
Yeah. And if you want me to write this down, so the PMF, this would do something like this, right? Half at x equals 1, half at x equals 0, and 0 at all other values. So let's go to an interesting problem then. So yeah, problem. Suppose x equals 0 with probability half, one with probability 1 by 4, 2 with probability 1 by 8, and so on. Okay. So essentially n with probability 1 by 2 to the power n plus 1, right? So here x can take on infinitely many values, right? But still countably many, right? So what is the expectation of x? So this is still countably many. So let's go to a new page. So essentially what we are given is x is 0 with probability half. Sorry. So infinitely many values, but still countable. So we need to find expectation of x. So what is the probability mass function? This is 1 by 2 to the power n plus 1 if non-negative integer and 0 otherwise, right? So expectation of x is 0 into half plus 1 into 1 by 4 plus dot 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 and so on. So this turns out to be 1, right? Why should this be 1? So do you know why? Okay, so let's see. So this sequence,
So
what should,
this is a arithmetic geometric
yeah, so
thing.
what do we do for this kind of sequences?
Sir, we multiply half with ex and then we divide it again. No, like subtract it from ex.
Yes. So essentially if it is something like this comes out from here, right? So if you write this out, then this is essentially 1 by 1 minus x, right? Now differentiate this. Differentiating this, you get 1 plus 2x plus 3x squared and so on. And this is 1 by 1 minus x squared, right? So what you were saying was correct, but this is essentially one step. You would be subtracting and then right two equations multiplying x with one and that, but you will need this technique very often from the after we move on, right? So we'll come to this. So but keep this in mind that this is for a geometric sum, right? This is true for a geometric sum. So differentiate this on both sides. So this comes out to be this, and this is essentially this, right? So this is 1 by 4 times 1 by 1 minus half square, right? It's 1. Okay. Okay, so let's try more problems then. So, okay, next problem. Suppose we roll a fair die if one or two occurs, we take x equals 3. If 3 or 4, then we take x equals 4, and 5 or 6, then we take x equals 5. Say 10, not 5, say 10. And yeah. So what would be the expectation now? So I define my random variable like this. So I need to find expectation of x. So what we have essentially is right. So expectation of x is summation x probability of x. So this should come out to be what? Just give me the value. No, this is not 4. This is not 4.
Sir, 1 by 3 times 3 plus 4 plus 5. So that is 1 by 3 times 12 and it's 4.
It's 10. Okay, yeah. So yeah, I told you it was 10. So okay, if you
Oh,
took my
x
10
was.
time, yeah,
Okay, sir.
yeah, right. So next example. So problem. Uh, Now let's take a discrete random variable which takes only positive integers as values. Okay, so say this is only positive integers. So say this is, what is expectation of x? And firstly say that why is this a probability distribution? Like,
Summation will be 1.
yeah, why is that?
So if we break it into like n plus 1 minus n, the
It's
numerator.
telescoping, right? So what is expectation of x?
Is it half?
Is it half?
1 by
No,
2.
no, it's not half.
Sir, is it n into n plus 1 by 2 minus 1?
So what will that be? mean, that is incorrect, but still.
So n by n plus 1.
N by n plus 1. No. I mean, just think about the definition once again, how I defined the expectation. I mean, someone told the definition of expectation, right? But using that definition, this won't work. But there's a subtle difference in the definition that is the original the definition of expectation. At least the interpretation of expectation. For at this point, I will redefine expectation after a few moments, after a few more propositions, say, because I need to define a few more stuff. But just take the definition once again. So, provided this sum converges absolutely, right? So, what is this essentially? So, have you learned about the sequence, right? 1 by n in analysis. Right?
Yeah, that diverges.
Yeah. So, what should be the expectation now? It's not well defined, and is it bounded? Okay, so before next class, just check this sequences, right? You need to check sequences and series a bit, because the convergence that you learn there, that would be used here in order to prove distribution. Like something goes to something in distribution, something goes to something in probability. So for those things, we need absolute convergence and the convergence of different series and things that we learn in analysis. So we need a bit of that. So this should be infinite, okay? And the expectation is not well defined in this case. So one good example of a random variable which is continuous, and I mean I have not defined continuous yet, but still where expectation is not defined like this, you can search it out. I mean it's a very nice distribution. So we'll also learn about that later on. Okay. So the next thing that I'll like to show is that expectation is linear. Okay. So what do I mean by that? I mean to say expectation of x plus y is equal to expectation of x plus expectation of y. Okay. So in order to prove this, need a slightly different notation for expectation. Right. So we defined expectation how? We defined expectation using the PMF. Right. Now let us define expectation like this. So if x is a random variable, on a finite sample space S, then we define expectation of x as summation omega belongs to S x omega times probability of omega, right? So, but we will not say that like we can show that the previous definition of expectation is same as this one, right? So problem, so I defined expectation like this, right?
Sir, can you show the previous slide once?
Yeah. So I'll write.
Done, sir. Thank you.
I'll write this next part down. So that's the problem. So I defined expectation of x like this, right? Expectation of x as summation running over x as that probability of x greater than 0. Right? Provided this sum converges absolutely. Now I redefined expectation, right? So now I defined expectation like this, that if variable defined on a finite sample space S, then expectation of x is this, right? So try to prove why they are equivalent. So okay, so I'll prove this. I'll prove the first one. So I'll give you a proposition next. Then you'll have to prove linearity of expectation. Okay, so let me prove this one. So for each I, for each I element of n, we denote the elements of the sample space. We denote by Si the events all those omegas element of S such that x omega is equal to xi. Okay. Now look at this. Si, the set Si's these are countable and they are also a partition of the space S. So what do I mean by partition? I mean disjoint sets whose union is S. Right. So now note that I said that here we are defining this on a finite sample space, right? So since we know that S is finite, since S is finite, all SIs are also finite, right? So since S is finite, SIs are also finite. Now we only have a finite number of sets SI which are non-empty, right? This implies finite number of set SI which are non-empty. Right? So let us write the expectation now as we defined earlier. So this is xi times probability which is summation, right? So this is again right. Intern is equal to so why we could write this, because we use the properties of the set SIs. Since sets were a partition of S. Right. Now you see I have deviated from the original definition by a bit. In my original definition, this was countable, right? So this should be true for countable also, right? So what if countable?
So one question.
Yeah.
Can you go to the previous slide?
Yeah. Yeah. Tell me.
Yeah. So that summation for the expectation. Why is it going to infinity? Like it should stop to the third last line.
Sorry. Which one?
Third last line. Yeah, those expectation you're writing there. That summation I going to infinity, right? So after some
This is fine.
say some t, no some so after some t value it should be 0, right? The x size.
Why?
Because we're taking a finite set here, right?
Yeah, but like you have problem with this n, right? So that's what I was going to say in the next slide by saying that you can actually replace this by infinity. Just think why. Like okay. So I understand your doubt, and it is true. I have written here infinity here, right?
Right.
But I have said finite here. So my claim is okay. So let me write this down. So my claim is the proposition is true for countable also. Proposition is true even for countable. As long as expectation of x is well defined. That I have defined earlier, right? What I mean by well defined. So yeah, I'll go back to the previous page. Now tell me why can I replace this with an infinite sum?
So here the random variable x of omega, since SIs are disjoint partitions, right? So after some value of I, say some m or some s, whatever it is, the value of the random variable won't be defined, right? Because there's no event. We've crossed the finite number. Like, so I don't understand how is this like
No.
well defined for the.
No, that's what I'm saying. I mean, you can replace this finite by countable. So
Okay.
countable does not mean finite, right? Countably infinite can also be there.
Hmm.
So that
Nope.
means that all I mean is that I can enumerate my set with 1 to n, like the set
Okay.
of. But that can be infinite also.
Right.
Now, if this is true for countable, then this is obviously true for finite, right?
Yeah.
So what I'm saying is I use the weaker statement to prove this, but generally this is true for countable whenever this expectation is defined, well defined. So what do I mean by well defined?
Okay.
I mean this. that provided that this sum converges absolutely,
Absolutely.
right? So
Hmm.
due to this condition that this sum converges absolutely, we need this identity because we have that this is well defined. So we have absolute convergence. Now just look at this summation I running from 1 to infinity xi times probability of x equal to xi equal to summation omega element of s now what what is this essentially? This is a rearrangement in the first sum, right?
Yeah.
Now since we have absolute convergence, so we have this rearranged thing also converging, right?
Yeah, to the same limit.
So if either the number of values of x or the sample space S is finite, we can use this argument.
Okay, I understood. I understood like your point. Like you're going from that countable and then proving that weaker finite statement.
Yes.
Is that
Because
correct?
for discrete, we will be
Okay.
needing finite only.
Mm-hmm.
And when we go to continuous, I'll be actually using I mean heavy machinery to prove actually these things because these won't be easily proved. You need
Okay.
something called monotone convergence theorem, dominated convergence theorem, and bounded convergence theorem in order to prove the convergence.
Okay.
Right. So we'll go to that while we learn continuous, but before that we need some discrete and discrete distribution. Right.
Okay. Okay.
Okay. So up to this is fine, right? So
Yeah.
we are doing this because we wanted to show linearity of expectation. So I'm writing this down explicitly. What do I mean by linearity of expectation? So if x and y are discrete random variables defined on a sample space S, so x and y are discrete random variables. So I'll write RVs from now on, discrete random variables defined on S, the sample space, and A is an element of real numbers. Then, so the first thing is expectation of x plus y is equal to expectation of x plus expectation of y that I have had written earlier. And expectation of ax is equal to a times expectation of x. As long as these expectations are well defined. Right? So just think about the proof. I'll start off with the proof in 2 minutes. Just think of about how we can approach this, like how we can prove this. We need these proofs. I mean, we need to learn about these proofs because later on you will see that in some problems you will need these basic facts because otherwise it's just basic calculation in some problems, and otherwise you need the basic. You need to come back to the basics. So let's think about how we can prove this. So I'll just give a hint. Think about it, how you can proceed, then I'll start off with the proof. Hint. Try to write x plus y as a new random variable z, right? Which is also a discrete random variable on the sample space S, right? So, and then we have this probability, that probability x equals x comma y equals y. We use this to denote the probability of the event that
So this will this random variable x plus y be necessarily defined on S? Like it could be not closed in that set, right? It could be something else.
like I have defined my sample space to be all non-negative integers.
Okay.
So yeah, I am talking about I mean, this proof will not work for continuous random variables. That's what I'm saying. So we need different things for that, but the same proof technique will work actually. So when you see the proof, you will understand what changes are needed in order to extend this argument for continuous random variables also. Like, you may not be able to define z always, but you can define something else. So let's just start off with discrete random variables first. So just a hint, like take x plus y as z, and I'm defining this probability. I mean, you can define this probability like the probability x equals x and y equals y. This can be explicitly written as this. So if you need to visualize it, like this is the intersection of these two events, right? Right. So essentially, what happens is uh, x takes a sequence of values, say xi. Y takes a sequence of values, say yi. Now we have defined z also. So say z takes on the values this. So since now observe, like we have all expectations to be well defined, right? So we can interchange the orders of summations because they are finite. So you know the law of total probability, right? I mean, you must know. So due to law of total probabilities, what can you write? You can write expectation of z equals right. Now we can change the summations. So that's what we'll attempt to do. So z is zk, then y should be zk minus xi, because I have defined x plus y as z. So now interchanging summations and writing, summing over all of them, we get, what do we get? We get k running from 1 to infinity, summation I running from 1 to infinity, summation j running from 1 to infinity, zk times probability of x equals x, y equals zk minus xi, y equal to yj. Now you see that this is a very absurd probability, right? So probability this would be 0, right? Unless zk minus xi is yj. Now for each pair of I and j, this will be non-zero for only one value of k, right? Observation. For each pair ij, this will be non-zero for only one value of k. Since zk are all different, right? Therefore, what can we write? How can we simplify the above summation? So we are stuck with this, right? For each I and j, we can write this, right? So we can write this as k running from 1 to infinity, xi plus yj, probability x equals xi, y equals zk minus xi, y equal to yj, right? So this is equal to, since only one has a value of this probability which is non-zero and other values of this probability are 0, this should be xi plus yj for that particular I and j times probability x equals xi, y equals 1, right? So we substitute this to the above sum. So we get right. So now let us break this summation, right? Summation xi. Right. So this is equal to summation I running from 1 to infinity xi now I take the summation inside value for that yj sorry yj so this is equal to now this was for finite, right? Like we have not used countability, right? So if we had countable sample space, then all these sums converge absolutely. So if we had countable sample space, then all these sums will converge absolutely, and we can justify writing this. So we can justify this like this. So we can read it and right? Now we needed to prove one more thing, like for the scalar one. So we needed to show that for a element of R, we have the following thing, which is summation the element of S. Since these are well defined and they converge absolutely, right? So, I mean, using induction on n, we can show that if x1 dot xn are random variables, then expectation of right.
So I didn't understand that. Why was that probability 0 in the previous slide? Couldn't follow that.
Where?
Except for one value you mentioned. Previous slide or previous 2 slides?
Okay. Here,
No, previous slide.
like this one.
Yeah,
Right?
yeah. You said it was 0 for everything, but only one value.
What is this? Here, y is equal to zk minus xi, and y is also yj, right?
Yeah.
And I defined this to be this. That is probability x equals x, y equals zk minus xi, y equals yj. This thing is the intersection of three events like this, right?
Mm-hmm.
So the last two events would be both conditioned on y of omega. So let me write it here. So wait. So I defined, so what would be the last intersection, right? So the last intersection would be like all those omega element of S for which y of omega, right? Y of omega is equal to zk minus xi. Intersection, the event omega element of S, such that y of omega is equal to yj, right?
Okay, this will be non-empty only if zk minus xi is equal to this yj. Okay, okay, okay.
And actually, there is a third intersection, but that does not matter because this will all give you the null set, right?
Right, right. Yeah.
Okay.
Okay, okay. Thank you.
Yeah. So, okay. So, using induction, we can show this for n many, right? Like if this happens for 2 and this one does happen for n many. So, let me give you a problem here. Problem. Suppose we roll a die. And let x be the value obtained. So we want to find the second order moment. So that is like we want to find expectation of x square. So find me the value. So everyone try this one. Try this problem. Everyone should try this problem. Like, so we had a lot of theory ongoing. So let's try this problem and then we'll again move on to some more theory. Because when I finish this off, then I'll be able to go to the problems. So everyone just text me in the direct message the answer. Direct message everyone please the answer. And once at least 4 or 5 of you have answered, I'll start up the discussion. Like yeah, and also some of you are answering this. So those who are answering this, so tell me, those of you who did solve something, gave me something. So tell me this, like this is essentially finding expectation of x square for a random variable, right? This is essentially finding out this. So what you guys said, what one of you said was something like this, like you wrote it out, but if I don't write it out, then it looks something like this, right? X equal to x, sorry. uh, right. So this is essentially I am writing it down. So I think most of you should be able to answer this because this is pretty easy. So y is equal to x square. Define the random variable like this. Then we have probability of y equals 1 equals 1 by 6. Probability of y equals 4 is equal to 1 by 6, and so on. So expectation of x squared is basically 1 squared times 1 by 6. What you wrote, right? So essentially this formula works. We feel like this works, right? So proposition, not a proposition, theorem actually. So the theorem is for a discrete random variable x, taking values and a real valued function defined and a real value function g defined on this set we have equation of g of x bracket right. So try to prove this one. Like for a real valued function g defined on this set, we will have this. Yes, and then Yes. So let me write it down. Before that, wait, I was trying to get to problem. So what all have you learned till now? Up to Bayes theorem, right? So conditional probability Bayes theorem, this has been done. Right. So okay. Okay. So we're about to prove this, right? Okay. Yeah. Yeah. So so proof. So let y be equal to g of x. Okay. Then we want expectation of y, which is equal to summation running over y times probability of y equals y equals summation y, right? This is what you meant, and you don't need to find them actually, because everything can be written in this form. Like we are running a summation over all y, where y is an element of the sample space, and we are taking all those x's. So we are essentially running the summation over everywhere. So this is equal to what we expected it to be, right? Okay. So okay, one more small thing, like expectation of x square is equal to summation running over the sample space. This, right? Now, say we take g of x equals c, which is a constant function. So we see that the expectation of a constant is this constant, right? So you can see, right, that if we take this will give me summation I hope, right? Okay, so let's look at this proof. So an urn cannot contain balls of different color. So, so this is a very famous proof where someone tried to prove that an urn cannot contain two balls of different color using Bayes' theorem, like conditional probability. Right? Just check out his proof. So here he says, suppose an urn contains two balls, each of which is either black or white. Thus, in the obvious notation, both of them are black. The probability of both of them being black is equally probable with the other four, other three. So they all have 1/4 probability. We add a black ball, so this becomes this. So everything has the equal probability because they have added a black ball to the first space. Next, we pick a ball at random. Then the chance of that ball is black using conditional probabilities is this. However, there is a probability 2/3 that a ball chosen randomly from 3 is black. Then there must be two black, one white, which is to say that originally there was one black and one white ball in the urn. So, what is the fallacy in this statement? Sorry, I wanted to mean same color. Yeah. So, of the same color. So think about this one. So this is a homework next class. Say, and let's try this one also. Let A and B be two events with probabilities. Probability of A.
So, can you show the previous slide?
Yeah.
So here, in the third line, we have written that the probability of three black balls, two black balls, and the last case is one black and two white balls. So, sir, their probability, I think, will become 4/8. So, what it should be 1/2.
Yes, but what's the flaw in this logic? I mean, in this particular logic, like why cannot you add something in front of the random variables like that and then have the same probability?
So, because then we are increasing the chances of one event, like here we are increasing the chances of black balls if we are adding a black ball.
So essentially, you are tampering with the sample space, right?
Yes, sir.
Yes. So actually, the sample space has changed here in this proof. So like, I want everyone to write a
Yes, sir.
detailed explanation of this. Like, just try to think of a detailed explanation. I'll tell this in the next class. I mean, uh, this should be very clear why this is not happening. Otherwise, there are many problems where you will face difficulty because uh, you have tampered with the sample space and you actually don't know where you have tampered it with. Okay. So just think about this problem, write it down or something, like write the proof down, or how this like this is known as Lloyd's proof. Okay. Okay. So have you guys heard of the Monty Hall problem?
Yes, sir.
Okay. So everyone, has everyone heard of this problem? Okay. So try to find this. Just wait a second. if you have seen the Montian problem, let me give you a variant. So let's try this one. Can you see the problem? Can you guys see the problem? A man possesses 5 coins. So can you see the problem? So this is an interesting problem. A man possesses 5 coins, two of which are double-headed, one is double-tailed, and two are normal. He shuts his eyes and picks a coin at random and tosses it. What is the probability that the lower face of the coin is a head? Now there's this is an extension. So he opens his eyes and sees that the coin is showing heads. What is the probability that the lower face is head? He shuts his eye again and tosses the coin again. What is the probability that the lower face is a head? He opens his eyes and sees that the coin is showing heads. What is the probability that the lower face is the head? He discards the coin, picks another at random, and tosses it. What is the probability that it shows heads? So essentially, this is uh, the whole syllabus of probability, right? So let's try this one. Like what I was talking initially. So we need these basic notions of probability and sets and axioms. So try this one, because after this I will be moving to moments. So we have covered till this in this class, right? So what I plan to do in next class, I'll write it down here. In next class, I am planning to do moments, variance, and CDF. Okay, and a lot of problems. So, and for those problems, I need a bit of, say, basic probability. So, yes. So essentially, yes. Both of you are saying same thing. Yeah, that is correct. The Lloyd problem is a basic fallacy. So you can also, I mean, this comes in. I mean, this is a famous interview problem. So you can keep this in mind or something. Yeah, and try this one. This is also another famous interview question. So try this one. And also this one. Just note it down. These three are homeworks. Okay. Because in next class I'll start off with the proofs of this and the solutions of this one, and then I'll go to moments, variance, and then CDF and a bit of problems again. Okay. So
Sir, can you please tell which book or source you are following? for the theorems or the theory part so that we can see the similar notations. It will be easy to understand.
Okay, so the book I am following actually is Sheldon Ross. Have you heard of it?
Yes, sir.
And I will also give you my own notes because I have my own notes from my college. So when I used to study in first semester, so I'm also using my own notes. So I can send you a PDF later on. I mean, after this whole chapter, I will send you notes, extensive notes of what I taught in class with my own notation, and you can find the notation everywhere. Like this notations would be found in most of the books. Like mm, this one, like how I am defining a set and this whole things. You can find this exactly this proof in Robert B. Ash. Introduction to Probability and something. So, and
Okay, sir.
this,
Thank you.
this is from Sheldon Ross. And one more book that, I mean, if you, I mean, the notations might vary, right? But the things will be consistent. So if you can understand, then I'll recommend you to try. So, like, there's a uh, course, MIT OCW course, okay, online. So there they have a book. Don't remember the name right now. They that
So
has some,
Joseph Lidden.
so that has some good problems. So you can try them, try those out. If you have problems with the notation, you can ask me. So like there are plenty of resources like that. So what I'll say is just follow one book like Sheldon Ross or um, Robert B. Ash or anything. Hoyle Portstone. That's one more book. So yes, this is actually conditional probability. Yeah, this is conditional probability. I just want you to give the answers of all of these. So about the books, so these are the books that you can follow. So what I'll recommend is just try stick with one book, and after we finish off with the theory, just check whether you whether I missed something or not, or whether there is something in the book that you cannot understand from what I have taught. So then we can discuss those. Okay. Okay. So first one is 2/5. Second is 1/3. What about others? The answer? Okay, so that this is a homework one. This is a homework problem. So try this out, and in the next class, I'll ask someone to tell me the answers. So because this is not from today's work, right? So let me end the class today with a problem by finding a PMF. Say, okay. So you have noted down these three problems, right? This is not. This is actually done. So these two problems essentially. So let me finish off with a basic probability question like say, okay, what distribution can I take? Okay, say x takes random variables, x is a random variable taking values in uh, okay, and the PMF is given by and sorry, I mean I write the lambdas in the opposite direction, so this is essentially lambda. Okay, so don't mind the lambda. So this is a positive real number. Okay, so what is probability x equals 0. Yes, this is Poisson. So what is probability x equals 0? Yeah, so I'll come to
E
this.
minus
This is a known distribution. I just wanted to check that whether you guys can apply the definition that I told today or not. So what is probability x equals 0? This is
E minus
e to the power minus
E
lambda.
lambda.
minus lambda.
Yes. So find probability x greater than 2.
So this is a complement case, right? 1 minus px0 minus px1 px2.
Yes. So that's the easy way out because the other way around is not so easy. So what he's saying is this is what you should do. Like
হবে বা কেন?
right. So this is right. So 1 minus e to the power minus lambda e to the power minus lambda square e to the power of minus lambda by 2. Right.
Yes, sir.
Yeah. So let me give you one more problem just before ending the class. So one more problem is let x be the number of insurance
এই
claims or
এরিয়াটা তো টিএম ইয়ে
the number
সিপিএম এরিয়া।
of insurance claims
তৃণমূল হলে তাও
a
একটু দেখতে
person
পাবে, সিপিএম বিজেপি হলে
makes in
দেখতে
a year. So assume that x takes the values 0, 1, 2, 3 and so on with probability x equals 0 is 2 by 3, probability x equals 1 is 2 by 9 and probability x equals n is 2 by e to the power of n plus 1. Find the expected number of claims made by a person, made by this person in a year. Expected number of claims made in a year. Okay, so let's end the class here today. Write this down. Just add this to your homework. So there will be 3 problems that I'll start off the next class with. So
That
I'll
is
start the
13.
next with this problem. Okay.
Sir, in the last term, that is 13 to the power n plus 1.
3 to the power n.
3 to the, okay, sir.
So what is the question here? Expected number of claims made by
This person
this person. Okay.
in a year.
Okay.
Okay. So I'm ending the class here today.
Thank you, sir.